If I am not mistaken, we ran out of time before we were able to talk about delta connected loads, so we're gonna knock that out really quick, tight 3 or 4 minutes. And then we'll move on to looking at balanced three-phase circuit analysis, which is the actual thing we're supposed to talk about for today's lecture. So delta connected loads. All right, so once again, we're gonna have the representation that I don't care for. So let's put terminal A up on top here. We'll put B right here. I'm going to call this Z delta A. Down here below, I'm going to put a node point. So this is where my C phase transmission line terminal is. The impedance connected between the B and C line will be Z delta B, and the impedance connected between C and A will be Z delta C, like so. Over here on the right-hand side, we will do a similar representation. Or I should say an equivalent representation. So if this is A, B, and C, that makes this guy Z delta A, this one Z delta B, and this one Z delta C. Let's see, looks terrible. All right, so what do you guys think our line voltages? Actually, excuse me, we do phase voltages first. Are going to be here. So it'll be the voltage drops over those three impedances, right? So I could call the voltage drop across Z delta A VAB like so. The voltage drop across Z delta B will be VBC like so. And the voltage drop across Z delta C will be VCA. So, and I can represent them on my alternative delta configuration over here as well. So we have VAB, VBC, and VCA. What about my line voltages? Same exact thing. VAB, VBC, and VCA. I'm going to go ahead and draw them explicitly as voltage drops across my transmission line terminals, but we can see incredibly easily that it's literally the exact same thing as our phase voltages. And then lastly, we have our phase currents. And so these will just be the currents that are flowing through those impedances. I'm going to draw them all such that they're flowing into the positive polarity terminal. So here is IAB, IBC, and ICA, or alternatively, IAB, IBC, excuse me, and ICA. So I believe I mentioned this at the end of our last class meeting, but these are literally the exact same thing that we saw for our Delta connected source, except that we're using capital letters for our subscript to denote that we are on the load side of our system. All right, so we have two different ways that we can connect our source and two different ways that we can connect our load. So that means there are four total permutations that we could see. We could have a Y-Y system where the source is connected in Y and the load is connected in Y. We could have a Y-delta system where the source is connected in Y and the load is connected in delta. We could have a delta Y system where the source is connected in delta and the load connected in Y. And lastly, we could have a delta-delta connection where both the source and load are connected in delta. So to start things off here, we are going to look at a Y-Y system. We are going to talk explicitly about what criterion needs to occur in order for our system to be considered a balanced three-phase system. And then we are going to use the results of our analysis on a balanced three-phase system to make some general observations about the behavior of a balanced three-phase system. So let's start talking about balanced three-phase systems. So like I said, we're going to start by looking at a Y-Y system. And this is going to be a three-phase four-wire system. So I'm going to explicitly include some neutral conductor here. So let's put my voltage source VAN here. My voltage source VBN here. My voltage source VCN here. And then I am going to explicitly include a neutral connection here. So this will be terminal A, B, C, and N. And just for the sake of argument, I'm also going to label this left-hand node N as well. But since those two things that are labeled N are connected by a short circuit, that is literally just the same node. Just showing effectively where the negative polarity terminal of those voltage sources are tied together at. Okay. Then over here on the right-hand side, I am going to draw my Y-connected load. So I'll call this ZYA. ZYB. And ZYC like so. There is my neutral connection on the load side of things. And just like before, I will call this node capital N. And now I'm going to connect my source to my load using a transmission line network. So my A-phase conductor will have an impedance that I'm going to call ZWA. Actually, I'm going to make that a capital A just so it's consistent when I'm writing impedances. This will be ZWB. This one will be ZWC. And our neutral conductor will also have some impedance that I'm just going to call ZN. So, like I said, we have a YY system here. So let's talk about the criteria for balance. So the first criteria, and we're going to work our way through the circuit from left to right. Okay. So we're going to start on the source side. So in order for our source to be a balanced three-phase source, we need the magnitude of our voltages to be identical. So that means that the magnitude of the voltage VAN is identical to the magnitude of the voltage VBN is identical to the magnitude of the voltage VCN, and probably won't do it here, so which is why I'm putting it in a different color, but we will later on simply refer to this as a phase voltage VP, where it's understood that anytime I use VP, I'm just talking about a magnitude of the voltage. I'm not worried about a phase angle or anything like that. That's why there's no bar over it, there's no tilde over it or anything like that. Okay. So magnitude of our phase voltages must be equal. That's the first criterion. The second criterion is that the phase voltages must have 120 degrees of phase separation. Well, that's supposed to be an A. So that means our angle theta BN must be theta AN. I'm going to put minus here explicitly because we are only going to be dealing with positive phase sequence sources in this class. However, realistically, the minus sign that you see here could realistically be a plus or minus sign, where if it's positive 120 degrees, it just means that we're dealing with a negative phase sequence source. Okay. So the phase angle for the voltage VAN is simply the phase angle of the voltage VAN minus 120 degrees. And theta CN would be theta BN minus 120 degrees, which is the exact same thing as theta AN minus 240 degrees. So if those two criterion are met, then our source is considered to be a balanced source. As we discussed in our class meeting on Monday. This will be effectively true for any commercially available three-phase generator or something like that we could ever get our hands on. That will also be true of the voltages that are present at the terminals of a transformer and all of that kind of good stuff. So this isn't something that we really have to worry about too terribly much. So now we're going to talk about our transmission line impedances. Okay. So in order for our transmission line impedances to be considered a balanced network, the impedances of our transmission lines have to be equal. So write that down. So that means specifically the impedance ZWA must be equal to the impedance ZWB, must be equal to the impedance ZWC, and we will commonly refer to this as just an impedance ZW. Now I want to put a note here. I'm actually going to bother to write it down. Our neutral conductor impedance, Zn, does not have to be equal to Zw for the system to be considered a balanced system. We're going to talk a little bit more about why that is in a moment. But if you, I don't know how many, if any of you guys have a copy of the NEC codebook, probably none of you at this point, probably many of you by the time you're a senior and you're worried about taking your FE and potentially your PE exams. But there are very different rules for sizing the neutral conductor in a three-phase system than there are for sizing your phase conductors. And the reason for that is that it is generally expected that your neutral conductor will carry significantly less current than your phase conductors. We'll see why that is shortly. So it doesn't need to be sized as large. So in a physical system, how would we ensure that our transmission line impedances ZWA, ZWB, and ZWC are equal to each other? Anybody have any thoughts on that? So these impedances are literally just representing a section of wire. So use the same wire and make sure it's the same length. That's it. So if you're going to use 4-knot wire with a stranded core and it's, let's say, 100 feet long for the A phase, then do the exact same thing for the B phase and the C phase, and you're good to go. It doesn't have to be any harder than that. Don't mix and match cable types. I guess technically speaking, you could mix and match insulation types, but that's probably not a great idea because they're going to have different thermal properties, and that might, since resistance changes as a function of temperature, that might not be super great. So realistically, just take all your wires from the same spool and install them simultaneously. Okay, so now let's go to the load side. Okay, so here's our fourth criterion. Load impedances must be equal. So this means that ZYA and ZYB and ZYC are all equal to each other. And so we'll typically just refer to this impedance as ZY. So making sure that all of our load impedances are equal is actually significantly more difficult. Okay, so if we have a piece of equipment that is designed to represent a balanced three-phase load, like an induction motor or a synchronous machine, then it's already taken care of for us. However, if we are presented with several different loads, we have to actively try to balance things. So I will try to describe verbally what this entails, or at least what I have had to do based on my career outside of education. So when I help to design battery energy storage systems that will be tied to the electricity grid, those battery energy storage systems usually have large three-phase HVAC units. Okay. However, the motor that runs the fans is a single-phase motor. So I will make sure that that motor, if I have a multi-unit installation, I will make sure that I put that motor on the A phase for every third container, the motor on the B phase for every third container, and the motor on the C phase for every third container, so that I'm just constantly rolling that motor's impedance between the phases for each different building, so that as long as I have a multiple of 3 buildings, it represents a balanced load. And if I don't have a multiple of three buildings, it's going to be extremely close to being balanced, because I'm not putting all of those single phase motors on the A phase or the B phase or the C phase. If I spread them out as evenly as I can among the 3 phases, then I'm going to be much closer to a balanced load as if I had just thrown everything on one phase. You can do that with lighting loads and all of that kind of stuff as well. So that's just a pretty simple and common sense way to do it. If you have multiple of the same thing, just put one on each phase, and then it winds up being balanced or close to balanced the more you do it. All right, so these are our 4 criterion for balance. So what we're going to do is we're going to start analyzing this circuit as an unbalanced system, which is a bit tedious, and then we're going to see what happens when we restrict the different aspects of this to be balanced, okay? So what we're going to be looking at principally are our line currents. So I'm going to go ahead and scroll up here and draw what those line currents are. So we're going to have a line current IAA. We're going to have a line current IBB. We're going to have a line current ICC. And I'm also going to put on here, and this isn't technically a line current, but we're going to use Kirchhoff's current law, and we have a 4th current. I'm going to call this current right here INN, representing my neutral conductor current. Okay. I'm also going to make an assumption here, and this is literally for mathematical purposes. You do not necessarily see this in a physical system. You may, but it's not always true. I am going to choose my source side neutral as a reference node for this system. So again, we may not have a physical connection to ground on the source side neutral. I'm just saying this is what I'm considering to be 0. So I want to, excuse me, I'm going to write a Kirchhoff's voltage, excuse me. So let me put down here, getting ahead of myself. Analysis. Okay. So we are going to apply KCL at the load side neutral terminal, okay? So if I look here, I can see that my line current IAA flows through the impedance ZWA and then flows through the impedance ZYA before flowing into my load side neutral terminal. The same is true of all of the other currents. So I'm just going to say that IAA plus IBB plus ICC plus INN is equal to 0. Anybody have any problem with that? Just good old Kirchhoff's current law from circuits 1. Okay. Now what I'm going to do is I'm going to apply Ohm's law in order to express these currents in terms of voltages in our system. So I'm going to draw a little KVL loop thing here. Let me put something. I'm going to draw this one in gray as well. So I'm going to call the voltage drop across my neutral conductor VNN, like so. Okay. So if I were to write a KVL equation for the A phase of my system, I would start from this neutral, go around in this way, and end back at that same neutral node. Okay. So what would the total voltage drop across the series combination of those two impedances be? Where is VAN in your equation? So I would have something like minus VAN plus IAA times ZWA plus ZYA, lumping those together, plus VNN is equal to 0. Rearranging that expression, I would wind up getting the relationship VAN minus VNN divided by ZWA plus ZYA is equal to IAA. And I would get a very similar relationship for my other two line currents. So that would be VBN minus VNN over ZWB plus ZYB plus VCN minus VNN over ZWB plus ZYC. And lastly, I have my neutral conductor current, which I can see very quickly that my current is flowing into the negative polarity terminal. So INN is going to be negative VNN divided by just ZN. I did, thank you. I'll fix that. Absolutely did. Okay. So we have effectively applied Ohm's law or Kirchhoff's voltage law. They're kind of the same thing in order to express our four currents in terms of those voltages in our system. Okay. So let's now say if ZWA is equal to ZWB is equal to ZWC is what we're going to call Z wire, and ZYA is equal to ZYB is equal to ZYC is equal to just a Y connected impedance. Then our expression can be reduced. So what I'm going to do is I'm going to move that minus VNN over ZN term, sorry, that should be a capital N there, over to the other side of the equal sign since it's the only negative thing. And so what we should see is VNN divided by Zn is equal to VAN minus VNN over ZW plus ZY plus VBN minus VNN over ZW plus ZY plus VCN minus VNN over ZW plus ZY. And now I'm going to move all of those VNN terms over to the left-hand side as well. So that's going to look like the VNN times 1 over Zn plus 3 over ZW plus ZY is equal to VAN plus VBN plus VCN over ZW plus ZY. Are we all okay up to this point? Okay. So if our source is balanced, then we should be able to determine the sum of those three phase voltages, right? So VAN could be expressed as, actually, let me do it this way without a magnitude there. VAN by itself times 1 angle 0 degrees. That's literally just me multiplying VAN by a factor of 1, okay? VBN could be expressed as VAN times 1 angle negative 120 degrees, right? That would mean that our magnitude stays the same, but our phase angle changes by exactly negative 120 degrees, which is what we would expect for a balanced three-phase voltage source. And VCN could be expressed as VAN times 1 angle negative 240 degrees. So if I factor out the common term of VAN, this is going to look like 1 angle 0 plus 1 angle negative 120 plus 1 angle negative 240 degrees. So I would like for one of you guys to grab your calculator and tell me what this thing is equal to. Zero. So that means that the sum of VAN plus VBN plus VCN is literally equal to 0. So popping back up here, I can just put equal to 0. So what does this imply? Okay. So I have VNN times 1 over my neutral conductor impedance plus 3 over the sum of my transmission line impedance and my load impedance is equal to 0. Have I at any point stated that any of those impedances are infinitely large? No. Generically, they could be literally anything ranging from a short circuit all the way up to an open circuit in terms of impedance. But we don't know where in that wide range of impedances they lie. So in order for the left-hand side of this equation to be equal to 0, that means that the voltage drop across my neutral conductor has to be 0. So in a balanced three-phase system, the voltage drop across my neutral conductor, VNN, and I'm putting 3 there to say it must be equal to 0. Okay. We can also look at something interesting here, which would be the current flowing through our neutral conductor, which we defined a while ago to be negative VNN divided by ZN. So how much current flows through our neutral conductor in a balanced three-phase system? Also 0. So this is a pretty interesting result, okay? So the voltage drop across our neutral conductor is 0, and the current flowing through our neutral conductor is 0. So since our voltage drop is always 0, we can effectively treat our neutral conductor as a short circuit regardless of what its impedance is, up to and including if it doesn't exist. Meaning if there's physically no neutral conductor there, in a balanced three-phase system, we can still treat it like a perfect wire. That is something that we are going to use in our analysis in a little bit to make how we analyze these circuits under balance conditions significantly easier. Okay, so now let's look at some other quantities. So let's look at our line currents, okay? So we have a line current IAA that we originally defined as VAN minus VNN divided by ZWA plus ZYA. This becomes, in a balanced system, simply VAN divided by ZW plus ZY. Now let's look at our line current, IBB. Our original definition was VBN minus, excuse me, this should be VNN over ZWB plus ZYB. In a balanced system, this looks like VBN over ZW plus ZY, but let's take this a step further. VBN over ZW plus ZY is the same thing as VAN times 1 angle negative 120 degrees divided by ZW plus ZY, which is literally the same thing as IAA times one angle negative 120 degrees. So the line current in our B phase is lagging the line current in our A phase by exactly 120 degrees. If we look at ICC, we would have VCN minus VNN divided by ZWC plus ZYC, which in a balanced three-phase system reduces to VCN over ZW plus ZY, where we could write VCN as VAN times one angle negative 240 degrees over ZW plus ZY, or IAA one angle negative 120, excuse me, negative 240 degrees. So our input voltages have the same magnitude, and the B phase lags the A phase by 120 degrees. The C phase lags the A phase by 240 degrees. And we see that in a balanced system, our line currents follow the exact same thing. Magnitudes are literally identical to each other. B phase lags the A phase by 120, C phase lags the A phase by 240. Let's look at a couple of other things here really quickly, okay? So get rid of this stuff here because we don't need it anymore. We're just going to talk our way through this without explicitly showing things, but here is our phase current, IAN, IBN, and ICN. What is the relationship of those phase currents to the line currents that we just determined? They're literally the same thing. So it stands to reason that our line currents, at least through our load, will all have identical magnitudes and will have exactly 120 degrees of phase separation because our line currents did. How are our line currents related to the phase currents in our source? IAN, IBN, and ICN. They are the exact same currents, except they're in the opposite direction. So they're just multiplied by one angle 180 degrees. So once again, we should easily be able to see that our phase currents in our source are also going to be equal in magnitude, but have exactly 120 degrees of phase separation. What if we wanted to look at the phase voltages across our load? So since all of our impedances are identical, and we know that the three currents that are flowing through them are equal in magnitude but have 120 degrees of phase separation, it should be very easily to say that our phase voltages at our load will have equal magnitudes and be separated in phase by 120 degrees. Slightly more difficult will be our line voltages. So let's figure that out really quickly here, okay? So if I were trying to find this line voltage, VAB, we're going to throw a little bit of math at this because we're going to wind up doing this several times. So this will just be a shortcut. How do you think we would solve for the quantity VAB if we knew VAN, VBN, etc.? So Kirchhoff's voltage law around that little loop tells me that here, our line voltage VAB is nothing more than VAN minus VBN. VBC would be VBN minus VCN, and VCA would be VCN minus VAN. So what we're going to see is that those three quantities actually wind up having literally the exact same magnitude and are separated by 120 degrees in phase as well. Well, let's prove that really quickly. Okay. So we did all of the others by inspection, but now looking at our line voltages at the load. So as I mentioned a moment ago, VAB is just going to be VAN minus VBN, which could be expressed as VAN times 1 angle 0 degrees minus 1 angle negative 120 degrees. Somebody tell me what 1 angle 0 minus 1 angle negative 120 is. Use your calculators. I don't expect you to know this off the top of your head yet. Square root of 3 angle 30 degrees. Thank you very much. That is absolutely correct. If we looked at VBC, that would be the same as VBN minus VCN, which would be VAN times 1 angle negative 120 minus 1 angle negative 240. Or VAN times what? So throw that in your calculator. 1 angle negative 120 minus 1 angle negative 240. Or 3 angle negative 90. Same magnitude, 120 degrees of phase separation. What do you think is going to happen when we do VCA? That's just going to wind up being VAN times root 3 angle negative 210 degrees. So all three of our line voltages will have the same magnitude, and they will all be separated by 120 degrees. What about the line voltages at our source? Well, V lowercase a, lowercase n, lowercase b, lowercase n, and lowercase c, lowercase n all represent balanced voltages as well. So those line voltages will also be a balanced set of voltages having the same magnitude and 120 degrees of phase separation. So not to beat this horse even more to death, but effectively, in a balanced system, every possible set of voltages and currents will also be a balanced quantity, meaning that they will have the exact same magnitude and 120 degrees of phase separation. So if we know what's going on in the A phase of our system, we don't have to really do any work to figure out what's going on in the B phase of our system. We simply subtract 120 degrees. If we know what's going on in the A phase, we don't have to do any work to figure out what's going on in the C phase. We just subtract 240 degrees. So all we really need to be able to do is analyze one phase of our three-phase system, and we can figure everything else out simply by shifting the phase by the correct amount. So that brings me to our next topic, which is what's called the single-phase equivalent circuit. So here's where we're going to bring in that relationship that I mentioned earlier. If the voltage drop across our neutral conductor is always zero for a balanced three-phase system, then we can actually come up with three equivalent circuits for our three-phase system. Okay? So our A phase would look something like this. So here is my lowercase a terminal. My lowercase n terminal, and this is my voltage VAN, seen between my lowercase a and uppercase a terminals is my impedance ZW, seen between my uppercase a terminal and my uppercase n terminal is my load impedance ZY, and seen between the lowercase n terminal and the uppercase n terminal is a short circuit. Regardless of whatever impedance is actually there, it's a short as far as we are concerned in a balanced three-phase circuit. Okay. I could then draw a balanced, a single-phase equivalent circuit for the B phase, which is going to be the same damn thing, except that I'm going to put VB in here. And similarly, here is my C phase equivalent circuit. Oh, excuse me. Lowercase c, uppercase C. So let me ask you guys a question. Based on your roughly 5.5 months worth of circuit experience at this point, how comfortable do you guys feel in your ability to analyze one of these single-phase equivalent circuits? I hope you can do it in your damn sleep at this point, because this is a joke, right? So we have taken this gross, terrifying looking three-phase system and simplified it down to an absolute joke. Okay. Now, there are some limitations here. Okay. There are only certain quantities that we can directly calculate by using our single-phase equivalent circuit. And they have to be quantities that actually show up here. Okay? So let's talk about what those might be. So I think we could all figure out how to determine a line current. Okay. So IAA or IBB or ICC should be pretty straightforward. So I'm just going to put a note here. Line currents. And then just for the sake of argument, let's talk about how we would do that. So somebody tell me how we would solve for the line current if we knew VAN, ZW, and ZY. Other way around. Ohm's law. It's still Ohm's law. So our line current IAA would be nothing more than VAN divided by ZW plus ZY. Okay, I agree with that. What about our phase current I capital A capital N? Same thing. What about the phase current through our source? Negative IAA. What about the phase voltage across our load? IAA times ZY. Okay, I got no problem with that. If you wanted to do it directly without calculating the current, this looks like a voltage divider to me, so we could also just as easily say that it's going to be VAN times ZY over ZW plus ZY. Right? So we can use a single phase, yes. They're the same damn thing. Yep, so it could be that, but they're the same damn thing, yes. Fantastic question. So this is just for a YY system. So we're going to work a brief example here to show how wildly easy this is. And then what we're going to do, and also talk about how we can solve for things that don't show up here. And then what we're going to do on Friday is learn transformations so that we can make any delta connected load look like a Y connected load and any delta connected source look like a Y connected source so that we can always use this easy ass circuit to do all of our analysis. Just as a heads up, I don't know how many of you guys have or look at other textbooks. Other textbooks or some textbooks prefer to do things in terms of delta systems and all of that kind of stuff. Not me. I don't see how it could ever get any easier than this. So this is how I do any and every balanced three-phase circuit analysis that I could ever want. Convert everything into a YY system and then just use simple transformations to figure out the quantities that I'm actually interested in. So anyway. All right, so let me find one of my example problems that's easy, but not too easy. Okay, this will be our last thing for today. So I'm going to draw a simple YY system. A, B, C. Here's a transmission line impedance. So let's call this lowercase n, this uppercase n. Let's say that VAN is 120 angle 0 degrees volts RMS. Our impedance ZW is 0.1 plus J 0.04 ohms. Our impedance ZY is 10 plus J 5 ohms. And our ultimate goal is to solve for our line currents and our line voltages at the load. So whenever I ask you guys questions on your homeworks, exams, etc., that is how I'm going to do things. I'm going to describe a circuit. I'm not even going to give you a picture 90% of the time. I will expect you to be able to draw the picture yourself because we've talked about what Y-connected sources, delta-connected sources, Y-connected loads, and delta-connected loads look like. I'm going to give you voltages or currents, some impedances, and then ask for quantities, okay? And the homework actually should be live, so you can look at it and see whether or not I'm messing around with you. I'm very much not, okay? So the first thing that I would do while we're acclimating ourselves to this balanced three-phase circuit analysis would be to draw a picture like this, and on our picture, identify our quantities of interest. So I'm going to only bother identifying our quantities of interest on the A phase because we know that if we can solve for the A phase quantities, we can get the B phase quantities by subtracting 120 degrees and get the C phase quantities by subtracting 240 degrees. So my line current would just be this current right here, IAA, and my line voltage would be this quantity, VAB. As we discussed a few moments ago, we can definitely get our line currents from our single phase equivalent. Our line voltages, we cannot do that directly because our single phase equivalent only has our A phase conductor and our neutral conductor. Nowhere does it have a B phase anything on it, so we can't really use that. Okay. So let's start by drawing our single phase equivalent circuit. So we're going to have 120 angle 0 degrees volts RMS. Zero point 0.1 plus J 0.04 ohms will go here. Ten plus J 5 ohms will go here. Short circuit goes here. And this is my line current IAA. So using the relationships from above, IAA is just going to be 120 angle 0 degrees volts RMS divided by 10.1 plus J 5.04 ohms. Or I just added those two impedances together because that's not hard. Nope, it's 10.1. 10 plus 0.1 is 10.1, right? So putting this into my calculator, I'm gonna do 120 divided by 10.1 plus 5.04. And I got, excuse me, that's scrolled too far. 10.631 angle negative 26.520 degrees. Amps RMS. What will IBB be? Great, you did exactly the work that I was expecting you to do. And by that, I mean practically none at all. Kept the magnitude the same, subtracted 120 degrees. There is no reason whatsoever to make it any harder than that. Somebody else tell me what ICC is going to be. So magnitude's the same. Angle will be negative 266.520 degrees. Amps RMS. Absolutely. So line currents, completely trivial. Now we need to sort out how we're going to get those line voltages. So a couple of minutes ago, we observed that our voltage VAB, the line voltage, was simply VAN minus VBN. Okay? I believe wholeheartedly that we can solve for VAN very easily using our single phase equivalent circuit, which means we should be able to solve for VAB as well. So even though we can't solve for it directly, we can solve for something that it's related to directly and then just sort the rest out. Okay. So what would VAB be equal to? IAA times 10 plus J5 is a perfectly reasonable way to do it. So 10.631 with an angle of negative 26.520 degrees amps times 10 plus J 5 ohms. I get 118.859 angle 0.045 degrees. Volts RMS. We don't even actually have to solve for, oh, sorry, that should be VAN. My apologies there. We don't actually have to solve for VBN at all. Right? So what I mean by that, we know that VAB is VAN minus VBN, which is the same thing as VAN times 1 ∠0 minus 1 ∠ -120. Hey, Sebastian, what's 1 ∠0 minus 1 ∠ -120 again? √3 ∠30. It is very much not 0. √3 ∠30. So, just gonna take my answer, multiply it by square root of 3 with an angle of 30. And I get 205.870 with an angle of 30.045 volts RMS. What would my line voltage VBC be equal to? Oh, what the hell just happened? VCA. How am I going to solve for VCA? Keep the magnitude the same, subtract 120. Oh gosh, negative 209.955, if my mental math is correct. Is it 209 or 292? 209. So we have analyzed a three-phase target for quantities of interest. Like I said, on Friday, we are just going to learn transforms that will allow us to make any non-YY system look like a YY system so that we can do the same basic circuit analysis for literally every three-phase system that we will encounter in this class. They'll all be balanced. All right, we'll see you guys on Friday.